Hello. Good morning, good afternoon, good evening, whenever you're watching this. This is week 11B. It's the graph theory presentation. I made the necessary corrections. I don't know how that happened, but it's posted properly now. So let's just get straight to it. What do we have here? Was it? I had it right there. Okay. So let's just start all over again. This is where we got to. We talked about the Königsberg problem. Okay. Is there a route which crosses each of the seven bridges exactly once? And not written here is and starts back where you began. If you started, say, this bridge, we just arbitrarily call A. So how we look at it is a schematic. So all the areas are big letters, and they end up representing the nodes, and the bridges are the edges. All right, which makes perfect sense. Now this is what a graph looks like. Um, for this particular um, problem. Okay. Oh, sorry, I just had to do something quickly. Back to this. So we we talked about this here. We begin at vertex A. Informally, how we do this. There's a formal way too, called an Eulerian path. And that's exactly the same as what we're doing here, but in formal terms. So each time you pass through any other vertex, you use up two edges, starting at A, and you want to end up back at A. Okay, so each node you go to uses up an edge. Okay, so here we go. It says it uses all the edges of the graph and starts and ends at A. Then the total number of arrival and departures from each vertex. Come on, each edge has a beginning and an end. Must be a multiple of two. And the degree of the ith vertex simply means, for example, the degree of D is 3, the degree of C is 3, the degree of B is 5, okay? The degree of A is 3. They're all odd. So, but the degree of B equals 5, the degree of C and D, these two, both are 3, and that's not even. What happened to A? How come we're not counting A? Well, because A is the starting point, so that's implicitly there. And if there were an even number of, if it was possible to get to A, there would be a total even number of the edge count would be even. Okay, so that shows. You might say, why is A not there? Well, once again, it's because it's implicitly there. We started there and we tried to get back to there, but we couldn't. So we have all these odd um, edges. The other way to present, this is very important too. That's something I didn't mention the other day. Um, we already know this business about the edge set and the vertex set. But here, what is the vertex set exactly? It's simply the cross product of vertex set with the vertex set with itself. This is a set of ordered pairs. That's the binary nature of graph theory. Graph theory deals with this problem of edges, which are binary relations. And it makes sense. So an edge is simply a subset of all the possible Cartesian products, edges, in other words. Okay, it is a subset of all the possible edges that can be produced. The ordered pairs, vi, comma vb. Simple graph. Okay, this is a simple graph. Simply, it has no loops. It has no double edges. Okay, so that's as simple as it gets. That is not a simple graph. It has multiple edges. This one has loops. Okay, so you have multiple edges or loops. Okay, that's an example. Now, a multigraph is a graph with multiple edges, two nodes connected by more than one edge. A graph with multiple edges, two nodes connected by more than one edge. And so that's right there. Look at that. That one too. Connected by, that's the one we're talking about right here. Two nodes connected by more than one edge. Okay, so right here, that's a multigraph. And of course, this is a multigraph. Okay, the one that we just discussed. Let's have a look now at this problem. An Eulerian path, in honor of the great mathematician Euler, is a path that uses all edges in a multigraph exactly once. Well, let's have a look here. Does that happen? A to B, B to D, C, or D to C, C to B. Well, I don't see how you can do it. Okay, a path that uses all edges in a multigraph exactly once. You just can't do it. So that's exactly the same thing that the conclusion we came to before. A multigraph exhibiting a path between any pair of vertices has an Eulerian path if and only if there are only 0 or 2 vertices that have an odd number of edges, leaving them. Well, there's no such thing here. The multigraph to the right has 4 vertices with an odd number of edges, leaving them, so it has no Eulerian path. 2 is not there. 0 is not there. Okay? Again, what we're looking for, any pair of vertices that has an Eulerian path is biconditional with there are only 0 or 2 vertices that have an odd number of edges. Well, 1, 2, 3, 4. Okay, there's no 0 edges and certainly no 2 edges. Okay, that have an odd number. So what do we have? Multigraph has 4 vertices with an odd number of edges, leaving them, so it has no Eulerian path. Okay, that's pretty simple. Fundamental types of graphs. Well, just a node by itself, or a finite graph, which is a bunch of nodes connected by edges, or an infinite graph. We're not going to talk about those. We've already seen the definition here. This is an undirected graph. This is a directed graph. An undirected graph doesn't have arrows. A directed graph has arrows. Warning! If you have double edges, like symmetric relation, if you have an edge going to, an edge going back, sometimes we just draw a line like this. So there's confusion in the literature. It is not an undirected graph if you have paired edges. Okay, but you use that for shorthand. It's just better if you use the directed arrows. So a degree of a vertex in an undirected graph is the number of edges incident with it, except that a loop at a vertex contributes twice to the degree of that vertex. The degree of the vertex V is denoted by degree. So this is the notation we already discussed. And so the degree of B is 5, degree of C equals the degree of D. We've already seen this already. I talked about it earlier, but here it's formally defined. Okay, and here is our first. Excuse me. Here's our first theorem, the handshaking theorem. Kind of get the idea? You're handshaking 2 edges coming to a node. The graph, V, E, let that graph be an undirected graph with M edges. Then the sum of the degrees of all the vertices is an even number. Note that this applies even if multiple edges and loops are present. Here's the crux. Each edge has 2 vertices. Like I said, each edge has 2 vertices. I started talking about it from the vertex point of view, but here, from the edge point of view, you can't have a dangling edge. It's kind of like a dangling modifier, if you know what that is. So here's the proof. It's very simple. We want to count the sum of the degree of vertices of G. So for the sake of proving an argument, we let the sum of these degrees equals of these vertices, the degrees of these vertices to be 0, i.e. we set the degree of all vertices to 0, and only then will we increment the degree if U is incident to E in part of the edge set. So let E1 be the first edge we choose. E1 is incident to Vj and Vk, which are both a set, part of the vertex set. And hence we increment each of their degree by 1. So the degree of Vj is 1, which equals the degree of Vk, right? We have 2 nodes and we have 1 edge. Note that if Vj equals Vk, then that's a loop. Not only can you have, an edge, but you can have a loop. Here's the node, okay? That looked weird. Then the degree of that vertex should be incremented by 2. For m, which is equal to the cardinality of E, we do the same process, edge 2, edge 3, all the way to edge m, incrementing the degree of the vertices incident to an edge. So we will notice that for every edge, we increment the total degree of the vertex set, or of course, this relationship, by 2, since there are m edges. We incremented the initially 0 value total degree of V by 2m, which equals 2 times the cardinality of the edge set. So that's proven. I mean, it's just simple. A lot of these theorems are like this, proved in such a manner. We begin with the trivial case, which is one vertex by itself. And then we start adding edges and noting that that's all this thing is looking at from the vertex point of view and looking at from the edges point of view, that they are consistent in building the handshake theorem, okay, proving it. I hope that made sense. So apply the handshake theorem to the following. What do we have here? So what is it now? We want to count the sum of the degrees of the vertices for the sake of proving it, so it should be an even number. That's what it says here. And so what do we have here? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Is that right? Oh, 18, I missed one. Okay, you get the idea. Number of edges is 9. 1, 2, that's the way to do it. 3, 4, 5, 6, 7, 8, 9. Oh, I forgot this one right here. That's why I blew it. I forgot this one here. I was too busy counting them in here. So that's the handshake theorem. So here you have a multi-graph, and you can see by counting the number of edges, you can apply the handshake theorem. Okay. Again, what is that? What is the significance of it? Let G be an undirected graph with m edges, then it's always going to have an even number of edges. The degree of the vertices is going to be 2m. All right. So that does not satisfy the handshake theorem, okay, because of this lone item right here. Okay. So there we go. That makes perfect sense. An undirected graph has an even number of vertices of odd degree. That follows from the handshake theorem. For example, is the graph with 4 vertices of degrees 1, 1, 2, and 3 possible? Okay, just think about the handshake theorem we just had. A graph with 4 vertices of degrees 1, 1, 2, and 3. All right. So 5, 6, 7. No, it's just not possible. So an undirected graph has an even number of vertices of odd degree. So that's not the case here. There's 4, but one has an even number. That violates it. So some definitions. A connected graph, you'll hear about this a lot. It's connected if for every pair of vertices there exists a path in the graph that starts at a vertex U and ends at a vertex V. So an undirected graph connectedness means that for any 2 vertices you can find a path, a sequence of edges connecting them. So that's a connected graph. So I just pick 2 arbitrary edges in the graph and I can always get to them. In a directed graph, connectedness is more nuanced. There's that word nuance we hear so much of today. We can have weak or strong connectedness. So a directed graph is weakly connected if the underlying undirected graph, obtained by treating all the directed edges as undirected, is connected. That's weakly. Strongly, if for every pair of vertices UV, there is both a directed path from U to V and a directed path from V to U. Okay, so you can get back. Remember, a directed path is going in only one direction. So there has to be another path that allows you to return to where you started. So you can't just replace these V's and U's, okay? Um, make it so-called invertible. It's not like that. It just simply means because these things are directed edges, they're arrows. I mean, these things are undirected. Um, but you've seen the case of a directed path. You can only go one way. So here, is there a way to go from here to here? Yes, there is. So this is obviously connected. Oh, boy, that was quick. I see. I see. Well, that's all I really wanted to do for this week. So you've had the end of oh Jesus, relations and functions presentation. That was a week and a half long. Plus that included the midterm. So that covered week 9 and 10, and week 11 had a continuation of the harder part, the denser part of relations. And now I've started chapter 11 and 12. Well, 11 is just simply this presentation. Do not look at the chapter there unless you're curious and want to learn more. But that's all we need to know about graph theory. So why talk about trees if you don't know what graph is? Because a tree is a special kind of graph. So we've done that now. And with that, we'll see you next week. Just keep up the good work. I mean, right now, this class is doing well. Again, I urge some people that are at the lower part of the distribution, just put in a lot of hard work. You can pass this course, even get a good grade, because I'll give you whatever grade you have in the final exam, the better of that or the some accumulated way that we tabulated it in the beginning of the course. How the distribution works: 25% for each midterm, 40% for the final, 10% for assignments, which I don't put much weight in them with AI hanging around these days. It's the only way to deal with it, in my opinion. But AI is a great tool. I mean, I used it, in fact, for you. Yesterday, I showed you a couple of question sets that were easily generated by YouTube. Sorry, by this crazy ChatGPT. You look for the errors if there are any, and I'll give you an extra point if you find one or many. I didn't check it over. I'd like you to. But of course, all you have to do is pump it into ChatGPT again and say, "Are there any errors?" Because it's that inconsistent. It'll make an error, and then it'll contradict itself in another pass. So it's how you prompt these things to give you a good answer. But anyway, it's a time saver, I believe, to use it. So in order to check these documents that I gave you yesterday, you'll have to actually work the problems out to make sure they're right. Don't just put them through YouTube or, ChatGPT. Just actually work them out. Yeah, we're doing well. Just keep up the good work. There's only a couple more weeks left, and the final exam is way at the end of April, unfortunately. So that gives us lots of time to prepare. Anyway, have a good weekend, and cheerio.